Water, fire, air, and dirt. Everyday magnets, how do they work? And I don't want to talk to a scientist, cause straight up magic is what this is.
That last clip was by the Insane Clown Posse. Not everybody has heard of them, but those who have definitely remember them. And as you can see, they sort of think that magnets are kind of magic. And while magnets are pretty impressive, and they kind of exhibit a force that you can't see, but there is absolutely no magic involved. And in fact, scientists and engineers understand magnetism so well, they can use those principles to create motors such as the one in your refrigerator or the one in your game console, even the one in your electric toothbrush. Last class, we talked about how the 19th century scientist James Clerk Maxwell discovered that electricity and magnetism are like two sides to the same coin. And in this class, we're going to talk about the magnetic field, and we're going to explore it in more depth. Have you ever considered how a compass works? It works because the Earth itself is a giant magnet. The outer core of our planet is made up of molten metal, mostly iron and nickel, and some lighter elements that are still being investigated. And the convection of this fluid causes a magnetic field. So we're surrounded by our own magnetosphere, and when particles fly at us from the sun, the Earth's magnetic field protects us. The magnetosphere protects us against solar flares by deflecting the flares' charged particles. However, while the Earth acts like a giant bar magnet, the magnetic poles are not the geographical north and south poles. The north magnetic pole is about 530 kilometers away from the geographic north pole. Furthermore, the pole wanders up to 80 kilometers per year, and the north and south magnetic poles even switch places occasionally. In fact, the last time they switched places about 780,000 years ago. And to add to the confusion, if you remember from last class, we discovered that the law of poles describes the interaction of magnetic poles. Opposite poles are attracted to each other, and like poles repel each other. Therefore, the north pole of a compass is attracted to the south pole of the Earth's magnetic field. And the south pole of Earth's magnetic field is really the geographic north pole. In order to describe the magnetic field of the Earth and other magnets, we must investigate some of its properties. First, the magnetic field is described by talking about the magnetic field lines. Magnetic field lines are very similar to electric field lines, which we have talked about before. Just as the electric field lines are not real and cannot be seen, the same is true for magnetic field lines. However, there are some rules for magnetic field lines. Magnetic field lines always run from the North Pole to the South Pole, and the lines never intersect each other, and the closer together they are, the stronger the field. As a quick example of how to draw magnetic field lines, we'll start with a bar magnet, and we draw the magnetic field lines so that they go from north to south, and we indicate that with arrows, again on the other side. And we continue with more lines, and this here isn't really crossing, but because the magnetic field lines are so close together, it indicates that this is where the field is strongest. And actually, the magnetic field lines go through the magnet and form closed loops, and they go in this direction so that they're going around in a circle, like so. These ideas are very simple in a bar magnet, but they can get complicated in other circumstances, like for an oddly shaped magnet. However, these magnetic field lines can be shown visually as though they are physical phenomena in certain situations. One way is by using iron filings and a magnet, or with a compass. The magnetic filings are not the magnetic field lines, but they are attracted to the magnetic field of the magnet and align with it in such a way as to look like the magnetic field lines. Magnetic field lines are also visually displayed in polar auroras such as the aurora borealis. This occurs when highly charged electrons from the solar wind interact with Earth's magnetosphere. Solar winds stream away from the sun at speeds of about 1 million miles per hour. When they reach the Earth about 40 hours after leaving the sun, they follow the lines of the magnetic force that is generated by the Earth's core and flow through the magnetosphere. All of this together shows that the magnetic phenomenon that were once thought to be magic can be explained by scientists, and engineers and others can harness that information so that we can create new advancements in technology and better understand the world around us.